Hey guys, today we're going to be going into a kind of new topic, and it's something called the normal model. So here we have a complicated looking chart. You don't have to look at that right now. Let's just consider a scenario. So let's say there is a pizza delivery service, and then their mean delivery time, so their average delivery time is 30 minutes. So you go and order pizza. How much time do you expect them to take to get to your house? So you're obviously going to say 30, but then it's definitely impossible that every single time you order pizza, the pizza delivery man is going to take exactly 30 minutes, right? They might take 29 minutes, 31 minutes, a little over, a little under, but you won't expect something like 4 hours to get your pizza. So this is basically the central theme of the normal model. When you have some scenario where there is an average value and then you keep on ordering more pizzas, so you get more data points, and they're not always going to be on top of the mean. So if you order 10 pizzas, your average delivery time for the 10 pizzas will be around 30, but each of the pizza delivery times won't be exactly 30. So one of your pizza deliveries may have taken 40 minutes to get to your house, while another one took 22 minutes. So that's what this is here. In this graph, if you took infinite pizza delivery samples, and then you put them all in a chart together, you just stack dots up on top of each other, it would end up looking like this. So most of the deliveries end up centering around 30 over here. So 30 minutes is your mean. However, you're still going to get some weird and unusual cases where pizza delivery takes way shorter than expected or way longer than expected. As you can see out here, some pizza deliveries went into 45 minutes or 15 minutes. And this is your normal model. It is a unimodal and symmetric model that is centered around a mean, and it's defined by the mean and the standard deviation. So the standard deviations are marked out here. Here it's 5. So 30 plus 5 is 35. So this is our first standard deviation, which is labeled up here. And standard deviations are abbreviated with SD. So because we're talking about a population, so every single time we order pizza, that is our entire population of results we're interested in, we denote the mean with mu. So that is our Greek letter. It's a weird looking U. And then our standard deviation is denoted with a sigma. My handwriting is a little bit weird. I put it more in a shorthand, so it's more of a triangle. If you see that, don't get confused, as it's still sigma. So the normal model has a special property called the empirical rule. Empirical. I think I spelled it right. So what it says is basically, once you label your mean and then you put out the standard deviations, so mu plus sigma and then mu plus 2 sigma, and you extend it out to 3 standard deviations. So there's another one over here. If you did the same on the other side and you have everything labeled, there is a pattern that happens, and this is true for all normal models. Between the first standard deviations, so between this line and this line, 68% of data points will fall in between the first standard deviations. Between 2 standard deviations, we end up with 95% of the data. And between 3 standard deviations, we have 99.7% of the data. So what this basically tells you is that anything outside of 3 standard deviations is really, really, really rare, because 99.7% of the data is already within 3 standard deviations. So it's the same thing for 2 standard deviations. If you go outside that, there's only a 5% chance of that happening because 95% is contained within the 2 standard deviations. So you can just imagine this model as a collection of little data points everywhere. So we took sample after sample, and then we made a big dot plot, and once we melded all the dots together, we got this curve. So 95% of the dots are within these 2 lines inside the curve. So here's some practice with that. Let's suppose the scores on a test are normally distributed, and the mean score is 80, and the standard deviation is 7. So we have a couple problems to look at. So what percent scored less than 87? What percent scored less than 73? More than 94? And then part D is a little bit different. So before we do anything, let's just look at the question. They said the mean score is 80, so we can label that as the mean value. That is always going to be your thing in the middle. And with a standard deviation of 7, we can calculate our other important marks. So 80 plus 7 is 87. Now we've gone out one standard deviation. If we go out another, we add 7 again. So 94, and then plus 7 again is 101. Now subtracting 7, we have 73, 66, and then 59. So now we can look at the question. What percent scored less than 87? First, where's 87? It's over here. It's our first standard deviation. We know that 68% of the data is contained within here. So within one standard deviation, there's 68%. And that means at the same time that outside of this one standard deviation, 32% of the data is still left outside because 100% minus 68% is 32%. And then we also know that this model is symmetric. So that means that the 32% is split evenly between the left and the right side of our little walls. So that puts 16% on this side and 16% on this side. Now the question asks, what percent scored less than 87? So that is everything to the left of this wall. So that means we can just add up 16 and 68% to get our answer. So that gives us 84%. So 84% of students theoretically scored under an 87. So the rest of the problems I'll leave to you guys. I will leave the answers in the description. So next we have the standard normal model. The standard normal model is a form of the normal model that's a little bit more special. So whenever you notate normal models, you always identify it with an n, and then in parentheses, you list out its mean and then its standard deviation. In the problem we just did, the mean was 80 and the standard deviation was 7, so this is how you'd write it. The standard normal model, on the other hand, is strictly defined as a normal model with a mean of 0 and a standard deviation of 1, and that is what I have over here. So this standard normal model is really useful for whenever you want to compare two things that are kind of unrelated. So most of you have probably watched Avengers or something from Marvel, I guess. I'll be honest, I have not. I'm a little bit weird. But let's say you want to compare the Hulk to the Flash. So the Hulk is like super strength, and the Flash, I believe, is he's a fast boy. Yes, he's a fast boy. So if you want to compare strength to speed, how would you do that? So this is what a concept called standardization does. Basically, you find some number, I won't give you the math for now, but you find some number that tells you how extraordinary the Hulk is compared to the average human strength. And then you find some number that describes how extraordinary the Flash is compared to average human speed. So once we get that number that shows how much of an outlier the Hulk and the Flash respectively are, we can then compare them using those numbers so we can see whose powers are really more extraordinary. In terms of how this ties into the normal model, we have a general normal model here. This could have any mean and any standard deviation. So let's say we have, again, the mean of 80 and then the standard deviation of 7. What we do when we standardize data, so when we get our number to see how extraordinary a data point is, we're basically taking some point on here and we're translating it onto the standard normal model. So that's what this is, mean of 0, standard deviation of 1. And then we take another distribution with a different mean and a different standard deviation, let's say 70, 80. We take a point on there, and then we translate it onto the standard normal model. And from here, we can see how really extraordinary these 2 points are, even if they're describing different things. So once they're both on this model, we can see which one is farther out from the mean. So it looks like this one is a little bit farther out, so that would make this point more extraordinary. So let's put that into math now. The number that we're getting and that we're comparing between the Hulk and the Flash is called your z-score. So your z-score is some number that you calculate with your data point and your mean, and then what you get out is what you're going to be comparing. So the formula for it is up here, and if you want me to write it into more human terms, that would be your z is equal to your data point, so this could be the Hulk strength minus the mean, so that would be the average human strength over sigma, so standard deviation of the population. So the standard deviation of human strength. And then we get some number out of there. So let's say we get 7 or something. So what this 7 means, it tells us how many standard deviations away from the mean that we are in the standard normal model. So if we got a 7, that would mean that the Hulk is 7 standard deviations away. So it's at the 7 mark. Let's just pretend this is a 7 and that this is to scale. So that means the Hulk is somewhere over here. And that means that he is a really, really rare data point because we already know that anything outside of 3 standard deviations is incredibly rare. Now let's say the Flash has a z-score. So that is what we calculate from here, of 10. So that means the Flash is 10 standard deviations away from the mean in our standard normal model. And because 10 is greater than 7, that would make the Flash have the more extraordinary power. So we can do some practice with this. Let's say we want to compare SAT scores to your score that you get in a math test. So SAT scores are on a 1600 point scale. So let's say someone gets a 1520. It's pretty darn good. And then you get a 96 on a math test. And you guys want to see which one of you is more extraordinary in your scores. So person number 1, let's say the SAT score for the time he took it, let's say the mean score was 1400. That's pretty high. And then the standard deviation was 200. And then let's say for your test, it was a really hard one. So the mean was, let's say, 81, and then the standard deviation was 10 points. So who did better? Let's check out person number 1 first. So we know that they got a 1520, the mean is 1400, and the standard deviation is 200. When we calculate their z-score, it's 1520 minus 1400 over 200. So from there, we get 0.6. He is 0.6 standard deviations away from the mean. So he is around here. Now what about you? So your score was a 96, and then the mean was a 81. All over 10. And then from there, we get a z-score of 1.5. So that means you are over here, and you are farther away from the mean. So you are much higher than average compared to the other person, and therefore you did better. So finally, there's some calculator functions that you should probably pay attention to. I will go deeper into these in my calculator video, but I'll give you a general overview of what they're for. So your norm CDF function is a function that you'll continually use throughout all of stats. And it's basically when given a normal model, let's say this is mu, and then mu plus sigma is over here, mu minus sigma is over here. What you do for the norm CDF function is you put in some lower bound and an upper bound. So let's say this is the lower bound and this is the upper bound. So we put in the number over here and the number over here into our lower bound and upper bound. And then we also put in the mu value and the sigma value. And what the function gives back is the area bounded by the upper bound and the lower bound. So what area of the normal model is within those bounds based on the mu and the sigma. So for example, if we had a standard normal model, let's pretend that actually looks good. then we put in a lower bound of -1 and an upper bound of 1. So you know that our 1 is 1 standard deviation, so the area within here should hypothetically be 68%, and then what we put into our calculator would be norm CDF with a lower bound of our area being -1, the upper bound of the area we want to find as 1, the mu or the mean of the model is 0, and then the sigma or standard deviation is 1. And then what it should give back is 0.68 because 68% of the data is within -1 and 1. Next we have our inverse norm function. This one is basically the opposite of the norm CDF function. So what that looks like is this. If you plug in an area, then it will go from -infinity up here until it feels that it has covered that area. So if the area you put in is 50%, so from -infinity, it counts its way upwards until it has reached 50% of the data values, and then it gives you back our value here. Since the normal model is perfectly symmetric, it will give you back your mean value, or in the case of the standard normal model, it will give you back 0. Let's call the area that you put in A, and let's call the number it gives you back X. So what this does is basically it gives you back a number X for which A% of the normal model is underneath it. So if we put in 84, so 0.84, 84% of the graph, then it would give you back some number X for which this side of the graph is 84%, and 16% is up here. And that is basically the inverse norm function. These will come in really handy once we go into probability. So that's it for the normal model for now. We will get into it a lot after chapter 17. So thanks for watching. I hope you learned something. Peace.